Hi all, this is Mr. Yeager for chemistry. Today we're looking at acid-base theories and then reactions and trying to break down and identify, I should say, the different parts of an acid-base reaction is what we're going to be doing. So, moving straight into it. We've already talked about basically the properties of acids and bases. That's what we covered last time, some of the terminology, monoprotic, polyprotic. Again, acid versus base with their colors. Obviously, again, seeing the picture on the side with phenolphthalein in there. So what we want to do a little bit more now is going, okay, so while we understand all these properties, how can I still, if I get a chemical formula, identify it as an acid or a base, or be able to predict whether I think it should be an acid or a base, okay? So we got a couple of definitions, and there's the guys that came up with the definitions. We have, first off, okay, we kind of are doing these in order. Our first definition was what's called the Arrhenius acid-base definition, or theory, if you want to say that, okay? The Arrhenius definition. This one is probably the one that is kind of easiest to identify, because Arrhenius stated acids are compounds that will donate H+, and bases are compounds that can donate an OH-, a hydroxide ion. So it's all about what they are giving away. An acid will always give away an H+, a base will always give away an OH-. So I say this is the easiest thing to identify because this means acids must start with an H and bases must end with an OH in the compound, okay? So, you know, I mean, giving quick examples, I have HCl. If I said, do you think this is an acid or a base based on Arrhenius' definition, it's clearly an acid. One, it doesn't have OH in it, and it's starting with an H+, all right? Same thing kind of goes with the bases, NaOH, okay? That shows you that it has hydroxide, and guess what? When you put it in water, it'll split up into sodium and hydroxide ions. Again, when I say donate, it's what is it going to give away based on what it is, okay? Now, the issue with this definition, you probably can think about it, is this definition forces those chemicals to have an H+ and OH-. And we know of chemicals that are bases that don't have OH-. One of the ones that's most obvious, not most obvious, sorry, one that we need to know is NH3. NH3 ammonia will, if I put it in, you know, if I put litmus paper in it, will turn blue. When I put phenolphthalein in it, it will turn pink, all right? And it therefore is a base. It has all base properties. Basic properties is what we'd say sometimes too. The problem is, there's no O in it. There's an H, and I think a lot of people, when they first see this, would go, you know what, I think that's an acid because I think it's going to give away one of its H's. It doesn't. It does not give away one of its H's, all right? You actually have to put an extremely strong base in ammonia to have it actually say, okay, fine, take one of these H's. It doesn't want to, it wants to hold on to it, all right? So NH3 is a base, so unfortunately Arrhenius' definition falls apart right there. It's still not bad. If it clearly has hydroxide, we know it will be a base, but we need to help identify more compounds. So the primary definition that we look at, more than any other one I would say, is the Bronsted-Lowry acid-base definition, okay? At least, again, in high school chemistry. The Bronsted-Lowry definition keeps the Arrhenius definition for acids. It still says acids will donate H+, okay? So we still hold on to that. All the acids we use are acids that start with hydrogen, okay? Hydrochloric acid, sulfuric acid, nitric acid, okay? Those things are all H and something else. But instead of saying that bases need to have an OH-, we instead say bases are chemicals that will accept an H+, which all OH- compounds will do. If I put an acid into a NaOH solution, the NaOH will actually pull that hydrogen off of the acid. It will accept it. It will pull it into itself. So this one we like a lot too, because then all we have to pay attention to is the hydrogen. All right? The chemical that loses a hydrogen is an acid. The chemical that gains a hydrogen is the base. And so we can easily look at a chemical reaction that way and make it a lot easier. All right. So this now includes NH3, because what NH3 will do if I mix it with basically, well, even just water, is it will pull one of those H's off of it and form NH4 plus, and then guess what? We'll form OH minus at the end. All right. So that kind of also confirms that we should have a basic solution. It's forming hydroxides in the water, even though it doesn't have any hydroxides. All right. So real quick with that, since I'm pointing these things out, we often say H plus is the acid ion. Okay. OH minus, when you see that present as a result of some reaction, is the base ion. And so that can help tell you as well whether there is a basic chemical. Again, this chemical itself might not have OH minus, but then helps form it in water. Okay? So the Bronsted-Lowry definition is stronger than Arrhenius, but we still ask you to solve for, identify Arrhenius problems as well. Clearly, an Arrhenius acid is also a Bronsted-Lowry acid. An Arrhenius base, it may, a Bronsted-Lowry base could be an Arrhenius acid or base, but could be something else as well. All right. So we can now include more chemicals. Now there is one more definition that I just want to mention, at least make you know, but I'm not going to test on this one. And that is the Lewis acid base definition. This one actually is the most complete theory or definition for acids and bases, because now you can talk about any chemical. We get rid of the hydrogen dependency and instead look at the electrons, which all elements have electrons. So it turns out an acid is a chemical that will accept a pair of electrons. It will accept a pair of electrons into it. I mean, think about that with hydrogen. Hydrogen is hydrogen plus. What's it want to do? It wants to get 2 electrons so it gets the full energy level. So that includes obviously all the hydrogen compounds, but it wants to accept an electron pair. Bases do the opposite. They donate the electron pair. So you can see why people get this one confused, because for Bronsted-Lowry, they're opposite, where acids donate the H plus, the bases accept it. For when we get to Lewis, we're looking at electron pairs, and that definition, or that verb, basically switches. So this allows any other chemical to now be classified as an acid or a base. For example, something like AlCl3. It doesn't have any hydrogens in it. It doesn't have hydroxide in it. But based on, that's why I chose this one, based on aluminum structure, it has the space for a pair of electrons to come on in. It's able to accept a pair of electrons in between its bonds, and therefore it would be considered an acid. Okay, it'll create an acidic solution where I could put litmus paper in it, and guess what? It will turn red or pink. All right. So, but like I said, I don't necessarily test on that. It's something worthwhile to at least know, because you'll see that moving higher up in chemistry. So that's the theories, and we're going to kind of come back to those in some of our practice problems, because a lot of times in reactions I like to go, are we looking at Arrhenius acids and bases? Are we looking at Bronsted-Lowry acids and bases in terms of how we perceive those? But we're getting to some of the quote-unquote chemical reactions now. This one's not necessarily the official chemical reaction. This is more just what we call ionization dissociation of acids. So this is a process where we like to show how an acid will donate its H pluses, okay? How it breaks into its component ions. And it likes to donate an H plus one at a time. So when we get the polyprotic, we don't donate all of them at once. They legitimately donate one at a time, because you'll see, I mean, we'll get to that in a moment, okay? So let's start off with the simple ones, the straightforward ones. The monoprotic acids, they're just one step, where basically you have HCl, a hydrochloric acid, and I say, please show the ionization of hydrochloric acid. All you do is you write HCl, reaction, and then split it up into its ions, H plus and Cl minus. So again, that's showing you that HCl will donate that H plus. The Cl minus, that's just kind of leftover. We're not too worried about that. The second one, nitric acid, H plus and NO3 minus. Okay, so we just break it up into its pieces. I mean, if I want to do one more just to make it sure we're clear, I could be like HF. Show the ionization of HF, H plus, plus F minus. Okay, so that's for monoprotic acids. For polyprotic acids, you need to break it up into multiple steps, basically one H at a time. All right, and that's actually what happens, because when you pull off one H plus, I don't want to say pull off, but one H plus is donated, the other one actually becomes tighter, more tightly held by the compound. It's more difficult to have that one be released by the compound. There's a greater strength in it because there's more negative charge now. So with H2SO4, you can see we do our first step where I take away one of the hydrogens, and now I'm left with just HSO4 minus. Okay, again, I'll write that out. It's HSO4 minus. Okay, then I bring that on down, and I do it again with the other H. And obviously the charge of the anion will go up because it's now losing a second hydrogen. Okay? But the big thing is, because I always have people that are like, why can't I just do H2SO4 produces 2H plus SO4 2 minus? Because that's not how sulfuric acid will actually donate its hydrogens. All right? We've seen this from experimentation. When we get to titrations, we can see where the pH will change significantly as you release each of these hydrogens. It'll hold in place for a while after you release one, and then at a certain point it'll release the other one. Okay, so it's all about the idea that basically what's happening is this first one is a strong acid, and then the second one here is a weak acid. Okay, and so it will not be able to dissociate as well because there's already so much hydrogen in the water. Okay, so that's another thing to think about. Again, there is some equilibrium going on here, so while I say it all gets donated, some of them will be pulled back onto the sulfuric ion there. So that's it. We do the same thing with bases, but I'm going to tell you we don't mess with those as much. But it would be the same idea where they would just break apart into its pieces. Okay? But that's an ionization. Questions? No? Well, here we go. The last part of this then is we want to break down what are called neutralization reactions. So this is the official chemical reaction of an acid and base. We are going to create new products. So there are two things we often do with acid-base reactions. We are going to be we're going to be identifying acid, base, and then something called the conjugate acid and the conjugate base. Following that, we will also do neutralization reactions. All right? So, what is a conjugate acid and base? So here's an example problem I have for you. So you can see I have hydrochloric acid, and it's basically been placed in water. What will happen is one of those hydrogens from the acid will be donated to H2O, which in this case, because it's accepting it, must be the base. Okay, so I'm going to already say, I'm going to write down A for acid. The water in this case is my base. Again, water is something that's amphoteric. We could see that it could accept, in other cases it might donate. Okay? But I've already identified now the acid and base, and they're always on the left side of the equation. We always have the acid and base on the left side. It doesn't have to be acid first, base second. It could be base acid. That's fine. H2O plus HCl. But because it donates this H, that means H2O now has 3 hydrogens. So we get H3O plus. Okay? H3O plus. And then the chlorine is left by itself as a chlorine ion. All right. What we're going to have to do with this ultimately, we already did half of it, is we have to identify acid, conjugate base. So we already found the acid and the base. Okay. Here's my definition. You know, you have to think about the Arrhenius and Bronsted definitions above. That's what I've been going through. The hydrochloric acid, again, if you know the name of it, that kind of helps. But clearly the HCl is going to be the thing that sends, I don't want to say clearly because H2O obviously has hydrogen first as well, but hydrochloric acid is what's going to donate to H2O, and H2O is going to accept. Okay, so those are my acids and bases. What I'm saying here is, while I can use the Arrhenius definition, I primarily use the Bronsted-Lowry definition. So, what do I then do? Okay, we already did that. We identify what happens to the two reactants. One will donate H plus and one will accept. All right, this is kind of breaking it down piece by piece. You should notice HCl donates its H plus to become Cl minus. H2O accepts an H plus to become H3O plus. Okay, I'm going to go ahead and mention it now, even though it's down below. H3O plus is an important compound to start recognizing. It is called hydronium. Okay, it is the hydronium ion. This is another version of what we could say is the acid ion. It's the water that has the hydrogen added onto it already. So you're going to see that quite a bit in these chemical reactions, all right, or these ones that we're going to be identifying the different pieces of it. All right, so that's hydronium. All right, so we got to this point. HCl is the acid, H2O is the base. Now for the conjugates, the acid will form the conjugate base. What I mean is what's left over of the quote-unquote acid is now the conjugate base on the product side. So the conjugates are always on the product side of the reaction. Okay? The acid will become the conjugate base, the base will become the conjugate acid. So it's kind of a flip-flop here. They have to switch. Okay? The whole purpose of conjugates is if the reaction went backwards, if we have a reversible reaction, those chemicals on the product side are now my acid and base, and you're going to see the opposite occur where the conjugate acid will give up the H, the conjugate base will accept it, and now we're back to acid and base on the reactant side. It's just the idea of I flip-flop the reaction, I can see which ones are still giving or taking the hydrogen ion. The biggest thing I would say with this is I usually use arrows to when I usually show this in class a lot of times, I use arrows to connect the acid with its conjugate base and vice versa. So again, you're in the video already, you're going to see this in a moment. I already mentioned this. H3O plus is the hydronium ion. You need to know that. Okay? So let's do some conjugate acid-base problems here. Okay? Let's actually go here. I'm going to start off with these ones where they're clearly given to you. All right? So I want to try to figure out the conjugate acid base of these different ones. Okay? So what I have here is I have KOH plus H2O forming KOH2 plus OH minus. So if I look at this, clearly KOH and KOH2 plus are similar formulas. The only thing moving is H plus. We need to find where one H plus moves. Well, KOH has clearly added an H plus. All right? It has accepted the H plus. If KOH has accepted the H plus, it must be the base according to Bronsted-Lowry if it accepts a hydrogen ion. From there, we can already figure this out where we can now say water must be the acid. If I already have the base, the other thing in the reactant side is the acid. And then I could keep going and say KOH. Well, it was the base. It turns into the conjugate acid. And that means OH minus must be the conjugate base. Now again, how can I make that connection so easily? Okay, I can go back and go H2O. What does that become? Well, it becomes OH minus. It's lost a hydrogen. Like KOH is gaining one. H2O is losing a hydrogen ion. Where does that go? It goes from the water to KOH. So H2O is my acid, KOH is my base. And again, if I use my arrows, one of the other things I say is you must have A, B, C connected on the arrow. Only one time. So you can see I have KOHB connected to Ca, KOH2 plus. A, acid, H2O is connected to Cb, conjugate base, OH minus. And again, the idea is if I happen to then go in the opposite direction, what's happening? The H plus is going from the KOH2 plus, which means that's my acid now. This is my base. And then I could obviously go on the other side and be like, well, now this is my conjugate base. This is my conjugate acid. Okay? If I had this in reverse. So that's all it is. Okay? It's basically, you know, which side are we, like, obviously we're always saying left is reactants, right is products. But if we happen to have it go in reverse, we can figure that out. So if I look at another one, okay, if I look at this one right here, I have HSO3 minus, all right? I'm looking for really paying attention to the second part because, again, I know one hydrogen is moving. Well, it's HSO3 minus, but then it becomes H2SO3. That means H2O must become OH minus. Okay? So now if I see that, okay, this HSO3 has added an H plus, that must mean this is my base, H2O is my acid, because they have to have acid and base on the left. The base turns into the conjugate acid, the acid turns into the conjugate base. And there we go. All right, let's look at another one. Let's go down here where we don't, maybe it's not as apparent. Like let's look at number 7, or yeah, let's look at number 6. So we get C6H5NH2. So we don't see the OH minus anymore. Again, when you see OH minus, like, and I said, you know, what definition can I basically go off of here? I could say this is basically off the Arrhenius definition because I see the OH minus, OH in it in some ways, okay? The OH involved. But going down to number 5 or number 6. What I see here, okay, I'm looking for where the hydrogens are going, and there's lots of different hydrogens here. All right, C6H5NH2. What chemical looks similar to that on the other side? The one at the very end. And that means H3PO4 and H2PO4 are our connections there as well. So what's happening? I'm going to look at H3PO4 this time. H3PO4 is losing a hydrogen to what? The C6H5NH2. It is donating it to the other one. So H3PO4 is my acid, which means C6H5NH2 is my base. My acid becomes my conjugate base. My base becomes my conjugate acid. All right. So that is conjugate acid-base pairing, trying to identify those. Let's just do one of these real quick. This is the ionizations again of a polyprotic acid. If I said let's show the complete ionization of H2SE, we would do HSE minus plus H plus. Then I'd bring the HSE minus on down and do it one more time. H plus plus Se minus 2. There you go. That's an ionization. Okay? So, going back, last thing to then look at is neutralization reactions. All right? So again, a neutralization reaction is always a reaction between an acid and a base. There are two things always true about neutralization reactions. One, an acid-base reaction will always be a double replacement reaction. Okay? So I think we're pretty good with those. Double replacement reactions. All right? We got the chemicals. They're going to switch partners. The other thing, though, that we already, I mean, that's the thing. We know it's going to be double replacement, but we also know then this second part's true. The products will always be H2O and a salt. Okay? There'll always be H2O and a salt for a neutralization reaction. If you forgot what a salt means, a salt is any ionic compound. Okay? It's any ionic compound. So not just sodium chloride, calcium chloride, lithium fluoride, etc. It's whatever ionic compounds left over there. The only other thing to remember is make sure to balance at the end. All right. One of the hints I usually like to give students is instead of writing H2O, write HOH on the product side, and then you'll be able to easily balance out the OH minus ions in the reaction. Okay. So I got a couple examples. Okay. I have NaOH plus HCl. It's going to be a double replacement, and I know it's going to form HOH water and then NaCl. All right, make sure you again write them in order, always cation followed by the anion. This one's actually already done then, everything's already balanced. 1 Na, 1 Na, 1 OH, 1 OH, 1 H, 1 H, and 1 Cl, 1 Cl. Now again, when I say 1 H, 1 H, I balance this OH together with this one, and then this H is separate. Okay, I know some people are like, well, why can't I just balance all the H's? Have a good time, get it right. Okay? So the second one, H2SO4 plus AlOH3. Okay, hopefully again you can clearly see I have an acid and a base. So it's going to be double replacement. Guess what? HOH plus AlSO4. I'm just bringing my ions over. This is not correct yet. I know HOH is correct, water, but then aluminum is plus 3, sulfates minus 2, crisscross, Al2, SO4, 3. So this one I got to balance. If I balance it, and again, this is why it comes in handy to do the OH separately, I got 2 H's, I got 1 H. So initially I might be thinking I need to put a 2 right here. I have 1 SO4, I have 3 SO4, so I actually need to come back and put a 3 right there. That changes my hydrogens already to, and again only looking at this first hydrogen, 6, so I need to put 6 right there. Well, now I have 1 Al, I have 2 Als. Put 2 right there, I have 6 hydroxides, I have 6 hydroxides. Okay? So again, I just say, I think it's easier, it's perfectly fine to write it as HOH. I've just seen people struggle where they write H2O plus Al2SO43, and they would sit there and go, okay, I have 5 hydrogens, I have 2 over here, so I raise it to 10, you know. That's where it can get a little confusing versus I could just say, pay attention to the hydrogens, okay? I'll rewrite it like this, the hydrogens, and then pay attention to the hydroxides, pay attention to the hydroxides. All right, so let's try just a couple of problems here, a couple more. I'll use this one. Let's try this one. All right, so not that one, I'm not doing that one. Okay, so write an equation for this one. It does also say identify the Arrhenius, Bronsted, and Lewis acids, bases, label conjugates if applicable. Okay, this one's not going to be a conjugate acid base. With conjugate acid base, we're always going to usually have water with it, so we can see the H3O plus and all that stuff. Okay, so what I have here is I have an acid and a base, and I'm going to form HOH plus KBr. That one's already done. Okay. I would say I would call this the Arrhenius acid then, and this is the Arrhenius base. So I would be using the Arrhenius definition primarily on this one, because I don't necessarily see that hydrogen being accepted by the other compound as clearly. So when you clearly see an H and an OH in a reaction, that's an Arrhenius definition reaction that we would look at there. Okay, let's find another one. Not that one. Not that one. Let's do, well, this one would be like a conjugate acid-based one. So this one we would have, it's like, again, how do I know that? Because it's not a full base, all right? We can't create the salt. That's when we know we're not going to do a full neutralization. So this one would be, in the end, HOH plus NO3 minus, okay? Now, if I said, let's identify conjugate acid, conjugate base. Now, we're going back to that problem. These two are clearly connected, and these two are connected. HNO3, I mean, we can kind of tell too, it's lost its hydrogen, so that must have donated it. The hydroxide accepted it. The water is then my conjugate acid, and the NO3 minus is my conjugate base. Okay. Let's see if I can find one more neutralization to do here. Nope, that would be another conjugate acid base one. I don't want that one either, sorry. I might have to go to something else. Yeah, let's just go to this. That's a base pair. There we go. Let's just look at a couple of these so you can see them. So I'm going to do ones where we actually have to balance it out. So H2, I'm looking at C. H2SO4 plus KOH. This is going to form H. I keep on not finishing the H. HOH plus KSO4. K is plus 1, SO4 is minus 2, so that's K2SO4. I have 2 H's, I have 1 H, so I need to put a 2 right there. 1 SO4, 1 SO4, 1 K, 2 Ks, 2 right there. There you go, 2 OH's, 2 OH's. So there's another neutralization reaction. If I jump over to this side, I'm going to do, push this out of the way. I'm going to do letter E, that's probably my last one. I'm going to form HOH plus AlPO4. Well, Al is plus 3, PO4 is minus 3, so that's actually balanced. I got 3 H's, so I need 3 over here. 1 PO4, 1 PO4, 1 Al, 1 Al, 3 OH's, 3 OH's. So those are basically other types of problems looking at neutralization. Okay? If this question then said, what definition is most apparent here? This one again would be the Arrhenius definition. Okay, because we see the OH and the H. Like this is donating an H, this is donating the OH in a way. Okay, so that's where we can run into that. If I don't see a clear donation where I see like through the conjugate acid base pairing where you can clearly see the H moving from one to the other, one donating, one accepting, that would be the Bronsted-Lowry definition. Lewis, I think I might have just said that. We're not going to use Lewis. All right, so that's about it. Thanks.